Welcome to the Journey Shake Cam. Well, we're getting very close to an assessment, so we need to do those warm-ups as quickly as possible so we can review them and make sure we understand these various ideas. Well, please do the best you can in that composition notebook, and we'll discuss them in a moment. In number 1, we are applying the concepts that we learned yesterday. Well, I would take out my blank periodic chart that's not so blank and follow the trends. Well, in the first case, we are asked for the largest size. Well, whenever I'm asked for atomic radius, I draw my little snowman who has a little head and a big body, and he always falls over in this direction. Well, when I look at these elements, I see that they're going from left to right, and therefore I'm going in this direction, and the largest is going to be the boron. Always refer back to what the question is actually asking rather than what I think that it's asking, because sometimes we write the wrong answers because we think about it too much, and we need to read the question. Now we're going for the smallest size, and we are going down the group, so we're going in this direction, and therefore the smallest is going to be my beryllium. Now C is the least amount of electron affinity. That would be the attraction that this atom has for an electron. Well, when I look at these 3 elements, and I specifically chose those 3 elements to illustrate the exception. Electron affinity is not a man-made scale. It is an experimentally determined value, and therefore when I see that this is an S2P3, I see that this arrangement is low energy. We have 2 electrons in the s orbital and 1 in each one of the p's. And therefore this is a very low energy arrangement and has the least amount of attraction for another electron. The largest electronegativity, well, this is a man-made scale, so it has no exceptions. I just have to look at the direction that I'm going, and I'm going from left to right, and therefore the greatest electronegativity will be the tellurium. The largest ionization energy, well, ionization energy is also an experimentally determined value. And when I look across these values, I see that I have S2P1, S2P2, S2P3, and S2P4. I must take a look at each one of them. Well, I see that this S2P3 arrangement is very low energy, and therefore it will not want to lose one of those electrons, and it will have the largest ionization energy. The lowest ionization energy is indeed that the trend is increasing from left to right, and I want to know the lowest, the least amount, and therefore it will be the sodium. And a question of this nature for 2 points for each one of these questions will be in your future. And that's how you do number 1. In number 2, we are asked for a variety of different things. Well, the first thing we are asked is a complete electron configuration. Well, I don't remember how to do that. I always have to write my diagonal rule. Well, I know on the first energy level I only have an s orbital, and any orbital can only have 2 electrons, and that would be the maximum is 2 for that s orbital. On the second energy level I have the p sublevel, and there are 3 orbitals in the p sublevel, giving me a maximum of 6. Then on the third energy level I have the d orbitals. The d sublevel has 5 orbitals, and therefore I have 10 maximum of electrons that can go in there. The fourth energy level has the f sublevel, and that has 7 orbitals, giving me a maximum of 14. Then the 5th, 6th, and 7th energy level follow the same pattern that the 4th energy level had. Then I draw a diagonal line through the first orbital, the second orbital, and then it will follow and guide me as to how the electrons will fill the lowest energy first. Well, when I look at my first element, it is bromine. And I find on the periodic chart that bromine has an atomic number of 35. It has 35 protons and 35 electrons in the neutral atom. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p5. 2, 4, 10, 12, 18, 20, 35. So I always want to double check that I've written that correctly. Then I like to do the ending electron configuration next because it gives me some information that is helpful. I do not consider the 3D because it is the outermost electrons I'm concerned with. Those are my valence electrons, the highest energy level, and therefore my ending here is S2 and P5. In order to determine the dots, I add up the S and the P electrons, and I get 7, and therefore I have 7 dots. Elements want to be S2P6, and we are at S2P5, and therefore bromine will gain 1 electron and have an oxidation number of -1 or -1. It is in the family of halogens, and it is a non-metal. Next we have calcium. Well, calcium has an atomic number of 20, and therefore it has 20 protons and 20 electrons in the neutral atom. 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. 2, 4, 10, 12, 18, and 20. Its highest energy electrons are S2. Its ending electron configuration is S2. It has 2 dots because of the 2 electrons in the S2. It will want to lose 2 electrons, and therefore it has an oxidation number or charge of +2. It is an alkaline earth metal, and therefore it is a metal. Then we have sulfur, and sulfur has atomic number 16. 16 protons and 16 electrons in the neutral atom. 1s2, 2s2, 2p6, 3s2, and 3p6. The ending electron configuration is S2 and P6. We add up the 2 and the 4, and did I say P6? I didn't mean that. 1s2, 2s2, 2p6, 3s2, and 3p4. Have to make sure that we get these things right. And therefore, my ending electron configuration is S2 and P4. When I add up those numbers, I get 6, and therefore I have 6 dots around my sulfur. This element wants to be S2P6, and therefore it will gain 2 electrons, having an oxidation number of -2 or -2. It is in the family of chalcogens, chalk formers, and is a non-metal. And then finally here we have helium, which is atomic number 2. We like that because it's short. It's just 1s2. Its ending electron configuration is S2, and therefore it has 2 dots. It has an oxidation number of 0, and it is considered a noble gas. And it is an exception in the noble gas because normally noble gases have an S2P6 arrangement. But helium is S2 because in the first energy level, when we take a look here at the first energy level, there's only an S orbital. And therefore, when we get those 2 electrons, we have a complete first energy level, and that is very, very stable. And that is what we call a duet. 2 dots instead of 6 or 8, an octet. It has 2, a duet and not an octet. It is a noble gas, and it is considered a non-metal. And that was a little bit of review. And now you and your facilitator will review the review worksheet, review the review and review, so that you'll do well on the assessment tomorrow. I know you will. It's the first one, and I know that's a little bit scary, but you'll be fine. And I know that you've been doing the process as we've been going. You've had lots of practice, and I'm sure that you'll do well. So make sure you review those warm-ups. They're always a good idea to review those before any assessment. Well, I wish you all the best, and I can't wait to see you tomorrow. Bye.
Thank you.